The dance of the spinning top. The phenomena called gyroscopic effect, angular precession, or rigidity in space have long been and remain evidence that generate amazement and attention. Although hard to believe, inventions like the spinning top, the diabolo, the Segway, the boomerang, or bicycle, effects such as stability on the constant vertical direction of a rocket after launch during ascent, the planetary precession of the equinoxes, and many other natural behaviors related to rotational dynamics, many of them ignored, represent unique obscure points reported as anomalies in texts on mechanics even today. During this audiovisual, you will have the opportunity to find out more about these surprising and curious phenomena, interpreting the innovative theory of dynamic interactions proposed by Professor Gabriel Barceló Rico Abello and discovering his equation of motion for rotational dynamics. The dance of the spinning top. Who has not seen what happens when you spin at a certain speed one of those toys known as a spinning top? The logical, natural, and immediate question of human reason is why it stays upright without falling to one side. You can find the answer to this question in any minimally rigorous document on mechanics in its rotational dynamics section. However, rather than simply repeat that content here, we are going to go a bit further. When a spinning top is rotating on itself, supported by the tip designed for this, and on a smooth surface, we can see that it does not need more than a single support point to remain upright without falling to one side, something that does not happen when the object stops rotating on itself, which is when we see how it falls to one side. This tutorial looks at what happens when, apart from rotating and staying upright, the spinning top moves horizontally over the surface. When this happens, rather than move in a straight line, the object takes a curved path without anything pushing it or drawing it towards one specific point or another. The fact that the spinning top moves from one place to another on the floor in circular motion is what we call the dance of the spinning top. Even if it seems incredible, it is a natural behavior for which there was no rigorous, precise, and specific explanation until today. As we all know, the spinning top has an intrinsic angular momentum when it spins. That is, it rotates on itself on an axis that passes through its center of mass. If the body rotates at significant speed on a vertical axis to the ground plane, it will stay in its vertical position. If it tilts slightly with respect to the vertical position, we can observe the phenomenon that is known as nutation. And if in addition to tilting, its center of mass moves horizontally, it will not move in a straight line, which is what, as already commented, is known as the dance of the spinning top. When the body has both motions, intrinsic angular momentum and linear momentum, and is subjected to a new non-coaxial rotation with angular momentum, its center of mass does not have rectilinear motion, but instead revolves around an axis located outside the solid itself without there being a central force. Why does the spinning top spin on that point in the space? Let us analyze this. There is an inertial field here generated by the interaction of gravitational field strength on the body, which we call gravity, a phenomenon as still unknown today as the attraction between objects and the Earth, and which gives rise to the weight of the spinning top, which we represent by its vector. That velocity field, shown on the solid, is generated by the torque, which is shown on the support point of the spinning top on the floor and on its center of mass, due to gravitational interaction. It is a field that represents the initial fall velocity due to the weight of the spinning top. But this itself is not enough, because the body would therefore fall according to the fields shown. Let us look in detail at one instant of this strip. Remember that the body rotates at a certain speed on itself. Therefore, a new fall velocity vector will be generated on each point of the mass of the spinning top, which, depending on its relative position, will have a different magnitude. Consequently, due to the intrinsic rotation of the spinning top, a new resulting fall velocity field is created, also anisotropic and offset from the initial. The initial fall velocity field, caused by the gravitational interaction, is shown in yellow, while the resulting velocity field is shown in blue. In my observations, the initial field moves and intensifies to a greater or lesser extent, according to the intrinsic rotational velocity of the solid becoming the resulting field. Two triads of vectors are shown graphically. The green triad symbolizes the reference system of the movement of the solid, with this vector v indicating the vertical line to the ground plane. Vector t indicates the direction of the movement of the center of mass of the solid, while vector r indicates the radial direction of the movement and points towards the center of the curve made by the spinning top in its dance. The yellow triad symbolizes the reference system without movement from the previous one, but rotated according to the inclination of the body relative to the vertical to the ground plane. This is the plane of solid rotation. One of the vectors of the yellow triad is normal to this plane, while the other two are contained in it. As indicated, the system is advancing in the direction indicated by the green arrow T. The blue field results from the movement of the yellow field due to the intrinsic rotation of the spinning top, with this having no effect. The theory of dynamic interactions of Dr. Barceló Ricoadello proposes that this velocity field, in blue, is coupled with the translational velocity field of the system, generating the curved path observed. The variation in time of the resulting velocity field, shown in blue, generates an acceleration field which can be interpreted as a field of forces, with this being the effective thrust that acts on the system. The theory of dynamic interactions uses field theory to explain an evident phenomenon overlooked both before and since Newton's contributions. This new dynamic theory allows us to interpret multiple phenomena to date not shown with the ideal rigor, such as flight of the boomerang. I have personally prepared numerous experiments, devices and prototypes to demonstrate this theory for empirical goals. These video sequences show some brush strokes. This theory explains that starting with a rigid solid body or a system of material particles which has linear momentum on one side and intrinsic angular momentum on the other, that is, rotation of the solid relative to an axis passing through its center of mass, and if we add non-collinear torque to the main intrinsic angular momentum, which may even occur from within the system itself, we are presented with something new for our understanding today. The center of mass of the system shows a variation in its initial linear momentum in terms of direction, that is, it shows a deviation from its initial linear path. The velocity fields generated by the so-called resulting torque or dynamic interaction torque comes about as a consequence of the joint action between the main angular momentum and the secondary non-collinear torque applied. The behavior of the velocity fields generated can be observed in the relevant deviation of this pendulum, in which the suspended body has a rotor with angular momentum and is subjected to non-coaxial torsion due to its weight. The dynamic coupling from the translational velocity fields is generated in the rotating mass of the pendulum, with the resulting velocity anisotropy generated by the weight torque. The trajectory obtained is therefore the result of algebraic sums of both velocity fields that couple or overlap. As already expressed, this theory was discovered in recent years by Professor Gabriel Barceló Ricoadello, who has dedicated much of his life to its research and dissemination through texts, tests, conferences, interviews, web pages, patents, videos, and books published in the field of physics and mechanical engineering. Unlike the boomerang, the spinning top is generally a solid of revolution, and although it also mathematically operates the rotation matrix proposed by Barceló in the equation of motion of his theory of dynamic interactions, there are more differences between the spinning top and the boomerang because the former does not have wings, does not interact with the wind, etc. During the flight of the boomerang, looking at its trajectory from behind, what causes the secondary inertial fields is indicated. The effect of lift due to the action of the wind on the attack of the leading edge together with gravitational interaction which acts on the center of mass of the system. As the body has an intrinsic rotation after launch, the initial fall velocity fields, due to the intrinsic rotation of the boomerang, are transferred to form the resulting fields, which ensure that the center of mass of the body diverts its trajectory. Returning to the dynamic analysis of the spinning top, as I see it when it dances, there is sufficient intrinsic rotation for the vertical components to the ground plane from the resulting velocity field to keep the solid upright. What is more, this vertical component helps the spinning top to slide over the floor during its advance. In the resulting velocity fields, the parallel components to the ground plane help the spinning top to dance and produce the circular path around the supposed vertical axis to that plane. I understand that when there is insufficient intrinsic rotation velocity, the angle of displacement between the secondary torque and dynamic interaction torque is less than 90 degrees, which means that the body becomes less vertical. This is the phenomenon that we noticed in the spinning top, which, due to the effect of friction, loses intrinsic rotation velocity, with its axis inclining until losing support on its fulcrum. Our work is the result of a private research project: observation, experimentation, analysis, and teamwork. We have devised a physical and mathematical model which we have experimentally checked and which explains the dynamic behavior of bodies subject to different simultaneous rotations. This model and the theory that supports it have many scientific and technological applications. With this video, we have wanted to describe and account for the behavior of rotating bodies when subjected to new non-coaxial rotations, as experimental proof and demonstration of the theory of dynamic interactions, and specifically to better understand something as simple but suggestive as the dynamics of the dance of the spinning top.